Hi everyone, welcome to my talk. Today I'm going to talk about reflection attack and NTLM reflection especially. A story of an accidental Windows RC. My name is Wilfried. I should be with my colleague Guillaume, but I couldn't be at Hexacon this year, but he's definitely part of this research. We both work at Synactive. We are doing red team and pen test exercise. So first, let's talk about the vulnerability. The vulnerability came out this year in June with a CVSS score of 8.8 and was described by Microsoft for a Windows SMB client elevation of privilege vulnerability. We kind of disagree with this qualification because we mostly think this is a remote command execution. Actually, the vulnerability can be exploited by any authenticated user. This is an authentication reflection type of attack. And it only works on machines that does not require SMB signing. So basically, every Windows machine except the latest versions. It was so trivial to find it and exploit it that at least 7 people or company managed to discover it and report it to Microsoft within a short period of time. Shout out to Red Team Pen Testing that were the first to discover it. I'm also wondering how many people managed to find it and exploit it without even realizing that was a bug. You will see why right after. Few words regarding research motivation. I was performing some research on Kerberos reflection attacks, and I remember that there's already some story from the past. For instance, there was a tweet last year that someone that said that Kerberos relay is actually way more powerful than the NTLM reflection attacks. And he illustrated a specific case last year at Black Hat Asia on Active Directory certificate services. There's also a long history of bugs related to NTLM relay reflection attacks. The first one was in 2008, then in 2009, and so on. Each time, it leads to privilege escalation or remote command execution, but it was patched by Microsoft. Before digging into the vulnerability, let me give you some core concepts, so everyone is on the same level to understand. The first one will be authentication coercion. Authentication coercion is when you force an identity, that could be a user or machine account, to authenticate to a control server. There are several ways to coerce a machine into authenticate to a given server. Some ways are deterministic, others are not. The most popular one is to perform an RPC service, to force an RPC call and force the RPC service to access on an arbitrary file share. Let's illustrate that. On the top, we have our target machine, and on the bottom, we have the attacker laptop. First, the attacker will perform an RPC call to our targets. It will discover the dedicated RPC service. For instance, there's few functions that can perform this kind of call. For instance, EFS, RPC, encrypt file servers. And we will specify a remote location by specifying UNC path convention. The machine will talk to the SMB client part. It will tell the SMB client to access to this remote file, and then we will receive a SMB connection to our attacker. On the attacker laptop, we'll host a SMB server. We will answer with please authenticate to us. And then the SMB client will proceed the authentication workflow and will receive an authentication blob. The next concept is authentication relay. Authentication relay is when you somehow force a client to authenticate to a controlled destination. And then you relay this specific authentication to another server. Here, we force the authentication from machine A, so the client comes back to our attacker machine, we receive the authentication blob, and then we relay this authentication blob to another machine on another service. This way, we can impersonate client on machine A on the service on machine B. There's a specific case which is called authentication reflection, when the relay is the authentication relay is the client and the server are on the same machine. So there's already few vulnerabilities related to this kind of attacks, and mitigation were in place to prevent the relay back to the same machine. Last concept will be Kerberos authentication coercion. NTLM attacks are already well known, but we're wondering, is Kerberos relay attacks possible? Actually, it is possible, but it has more requirements. The main difficulty is to receive a Kerberos authentication, which is an AP rec message, to a control IP. We know that Kerberos is usually DNS, and it's also using tickets with service principal name. For instance, with the following formats, which is the service class followed by the target, here CIFS/SRV1. The service principal name is constructed by the client based on the server hostname or fully qualified domain name, and the server hostname or fully qualified name are resolved through DNS, which is not under control for an attacker. So if we want to illustrate that, we use our attacker. We said that we want to coerce to our target, SRV1. Then our target will ask to the DNS what are the associated IP to the specific record. The DNS will answer with the IP to our target, here SRV1. And here, because the server and the target are the same, we did not receive AP rec incoming message, and we cannot perform the relay. So at start, it was a bit complicated, but fortunately, a well-known researcher, James Forshaw, discovered that a Marshall credential target information structure can be added to the end of SPN. And during the authentication process, LSAS will discard it before making Kerberos ticket requests. So basically, you are requesting a ticket for a specific service for CIFS, for instance, with a specific target. Here, CIFS, SRV1, that will be our target, following by the long base64 encoded string. That will be the Marshall credential target information. And during that process, LSAS will actually return the SPN that we want, CIFS/SRV1. And also, because Kerberos is working with DNS, one interesting thing is that that specific DNS record it can be valid. So how do we exploit it? First, we register that specific record for instance, on the Active Directory environment. It can be done by any authenticated user without any specific privileges. Then we coerce a machine into authenticate to our specific DNS record. It will point to our attacker IP, and it can be done through SMB. And then we receive the AP rec message for the SPN that we want. So now if I want to illustrate that, the start is the same. Actually, the start by adding the DNS record to the DNS. It points to our attacker IP. Then we force the authentication coercion to now our specific crafted DNS record. Then the client will ask to the DNS server what is the associated IP address. It will answer with the IP address that points to our attacker machine. And then now we finally receive our AP rec, the authentication block that can be used for Kerberos relay, with the SPN also that we want. OK, so now let's talk about the vulnerability discovery. We know that some check and protection against reflection may be based on names. So we try to fiddle with the target name during our coercion. And something interesting happened when we tried to coerce using, again, that specific record discovered by James Forshaw. I was performing some Kerberos reflection attacks. So to perform the coercion, there's multiple tools, but Petit Potam can be used on one of them. I previously added that specific record, and I gave an incoming authentication to my control IP, and I can use the specific dedicated tool from Impacket, which is called rbRelax.py, that will receive the authentication and relay it back to the same server. And while I was doing that, I get a weird, strange error message that said unsupported make type NTLM SSP. I was a bit confused because most of the time Kerberos is preferred over NTLM in Windows environment. And also, I'm using only hostname or FQDN, no IP addresses, so Kerberos should be preferred. So in order to understand and to debug that, I want to do the same, but instead of doing Kerberos relay, I want to use the tool dedicated to NTLM relay. And while doing that, I will also start Wireshark and perform some traffic network captures. So basically, I'm doing the same. The coercion is the same command. And when I start the NTLM-Relax.py tool, I was quite surprised because at first, I noticed that the authentication succeeded, and also it gives us a privileged SMB session. So at first I was wondering it should not be working because reflection attacks are patched by Microsoft. It should not be working. I know there are some specific settings, for instance, registry key, that can allow this specific behavior, but it was not set in my environment. I was a bit confused, so I asked to a colleague to test on his own environment, and he was thinking, when I said the exploitation, he was thinking, no, you must be bluffing, this cannot be possible. You have a weird, strange settings, it shouldn't work. And then he tried, and he acknowledged it, and he said, okay, what the fuck, it works. So this is basically an accidental discovery. But we have few things to understand. We cannot let this vulnerability like that. We have to understand why does it succeed and why is it privileged. So let's dig into the root cause. So I was performing network diffing, and during the NTLM exchange, we have few steps. One of the steps is the NTLM SSP challenge. And on the left, you can see that we are forcing the authentication. We are performing coercion using the IP address, and on the right, we're using that specific DNS record. And during that exchange, we can see two differences. We can see during the flags that one is not set when using the IP address, and on the opposite, it is set when using the specific DNS record. Also, we have a result field that is empty when using the IP address on the bottom, and it's not empty when using the specific DNS record. And basically, it stands for standard local NTLM authentication on the left, and on the right, this is a specific case for local NTLM authentication. The flag that is not described here in Wireshark stands for local NTLM authentication. So we have to understand what is local NTLM authentication. First, the client will perform initialized security context. It will discuss with LSAS and the dedicated provider, so here NTLM SSP. The authentication workflow will go through. The NTLM SSP will answer to the client with an NTLM negotiate message, and then the NTLM negotiate message will be forwarded to the service. Again, we are in the case of a reflection attack, so everything works on the same machine. Next, the service will also discuss with LSAS. It will perform accept security context, still during the NTLM negotiate authentication workflow. And it will create within the memory of the NTLM SSP a local context with a specific identifier, here for instance 10,002, that will be used later. The workflow continues. The provider will answer back to the service with the NTLM challenge. It will also specify this specific context ID, and it will be forwarded back to the client, again with the specific context ID. Moving on during the authentication process, the client sends the challenge, but within the message, it also provides the context ID. It will be forwarded to the NTLM SSP. And within the memory, the specific context ID can be found. And now the token handle for that client will be added within the structure. The workflow continues. The NTLM SSP answers back to the client with the NTLM authenticate, again still referring that specific context ID, 10,002, and the client forwards it to the service. Last part of the NTLM authentication, the service will discuss with the NTLM SSP. It will perform NTLM authenticate, still referring the specific context ID, which can be found within the memory of the NTLM SSP, and now that will match a specific token handle tied to our client. And here, we can see that the authentication will succeed because it finds the context ID. It can use this specific token handle. So the authentication will succeed, and now the service can impersonate the client by using this token. So when I was performing network diffing, we know that we are relying local NTLM authentication over the network. But why does the server decide to perform local NTLM authentication? So we have to go into the SMB client authentication workflow. How does it work? First, the SMB client will connect to our specific crafted DNS record that will point to our attacker machine. It will perform then initialize security context. It will discuss with the ksecgd driver within the kernel. Then the driver will perform an RPC call to LSAS. Then, as I mentioned previously, LSAS service will discard the marshal structure information and transform the SPN with the base64 encoded string toward the SPN that we want. So it will perform LSAP check marshal target information. Then moving on, the LSAS service will discuss with the dedicated provider. It will perform SP init LSA mode context, and then it will be used by the client. So here we have something that we can call NTLM client local authentication hinting, where the client needs to decide whether he needs to hint the server to perform local NTLM authentication or not. Let's illustrate that. Previously, when we tried to perform reflection attack, we are using an IP address. So we have our SPM with the following format: class name followed by the IP address. SSPR get target source name will isolate the IP address, and then there will be some checks that will be performed. The first one will be if the target here, the IP address, is either the host name of the machine, the fully qualified domain name, of the specific string localhost. Here it's not the case, so it will also check if the target IP here is one of the local IP of our target machine. It's not the case again because it points to our attacker IP. So the client will not hint the server to perform local authentication. On the opposite side, when we are using the specific crafted DNS record that will at the end be transformed into that specific SPN, that our targets, SRV1, it will continue for the same decision workflow. And here is the target either the host name of the machine or the FQDN of the localhost? Yes, in that specific case, SRV1 matched the host name of the machine. Then it is asking if you are requesting a null session. No, it's not the case. Are we providing explicit credential? Here we did not provide any username and password, so the client will hint the server to perform local authentication. So when we are analyzing that with Wireshark, during the first exchange of the NTLM authentication workflow, we can see that within the NTLM negotiates message, we have two fields. When we are not performing local authentication hinting, those two fields are empty, which are calling workstation domain and calling workstation name. And on the opposite side, when we are performing local authentication hinting, those two fields are now filled with the dedicated value. Here, for instance, SRV1 and Asgard for the domain. OK, so now if we summarize everything, we know that LSAS discards the credential target information. So our long SPN goes back to our target that we want, SRV1. The NTLM SSP client identifies that SRV1 is the local machine. So the client will hint the service to perform local authentication. And then we move back to the NTLM SSP server that will perform the local NTLM authentication. But there's still one question that remains. We saw that authentication is working, but why are we privileged on the machine when the relays succeed? Actually, the SMB clients run in the system process, which runs with as anti-authority system identity. And as I mentioned previously, it will use the token of the client, so the SMB server therefore impersonates the token of anti-authority system. And for instance, with NTLM Relix, by default, it will dump the registry hives, but basically we can perform any action that we want. Let's illustrate that with a quick demo. Here, in the specific case, I will start NTLM Relix. I will just start with the option -E to execute a specific binary. It will be a reverse shell that will connect to our attacker IP. So at the bottom, I will just start a netcat listener, listening on port 443. And on the right, I will just perform the authentication coercion with a low privilege user using that specific crafted DNS record, here dedicated to a workstation following the base64 string. I'll start the authentication. On the left, you can see that the authentication succeeds. It tries to find, with the specific exploitation, it tries to find a writable share to write the binary, then start a service that will execute it. So I managed to find the admin $share to write it. It executes it. We receive an incoming shell as anti-author system on the dedicated workstation. OK, so we saw the case of NTLM reflection. But what about Kerberos? I'll start the research was about Kerberos reflection attacks. We discovered that the reflection also works for Kerberos. But if you remember well, when I tried this at the start, I got the weird error message that's saying that he wants to try the NTLM, to use the NTLM SSP provider. It is because the SMB server must not advertise NTLM. Otherwise, the negotiate SSP will select NTLM over Kerberos for local authentication. So what we can do also perform Kerberos reflection. The workflow is similar. We can use that, again, the specific DNS record. It will talk to the SMB client. The authentication blob will be an IP rec for the SPN that we want. It comes back to our Docker machine. Then we relay it back to the SMB service. Here it will succeed and also will be privileged. Let's understand why. The SMB client runs as anti-authority system. Network authentication is done with the machine account using Kerberos, so SRV $1, and yes, we are relaying the machine account. One thing to note is that the machine account is not privileged on this associated machine. So why does the reflection give us a privileged SMB session? This is because we have a specific workflow for Kerberos on lookback. This workflow is only applicable to anti-authority system clients. There's some specific parts of the code that checks if it's only system identity. First, the client will perform initial security context. Again, it will discuss with LSAS with the dedicated provider, here Kerberos. It will create a subkey entry within a list of the memory of Kerberos SSP. Within this subkey entry, we can have a structure that contains few information, such as the logon UID that refers to system. We have a subkey. This is a randomly generated cryptographic key, and a token handle that is associated to the system identity. The workflows continue. Kerberos SSP will answer back to the client with the IP rec. It will also provide the subkey within this ticket. Moving on, the client will send the IP rec to the service, again specifying the specific entry ID. The authentication workflow continues. The service will talk with LSAS and the associated provider. It will perform accept security context and also specifying the subkey. This is here that comes the interesting part. If the client name extracted from the tickets, so the IP rec, is the same as the local machine, so here SRV1 will, the SPN which has CIFS/SRV1 will match our target. The Kerberos SSP will check if the subkey contains within the ticket match one of the subkey entry list within its memory. And if it does, the authentication will succeed, and it will use the associated token handle contained within the structure, which here is the anti-authority system identity. So that explains why the authentication is privileged. Last thing is regarding patch analysis. So Microsoft released the patch in June of this year, and we were wondering where to look for. Does Microsoft patch for each protocol? Do we have one patch for NTLM and one patch for Kerberos? So we were wondering where to search. We remember that the vulnerability was described as the Windows SMB client elevation of privilege. So we were wondering, OK, maybe we should start by looking at the client code. Also, when we try to replay the attack, we notice that we are performing the authentication coercion. It does not come back to our control server. So we definitely look into the client part. So SMB client is partially implemented into the MRX SMB sys driver. So we do a bit of patch diffing of this driver. We notice there's a new check added in the function SMB SE create SRV call. This function is called when you try to access to a resource using SMB protocol. And basically what it does is it adds a new check, and if the target name contains a marshal target information, it will abort the authentication and you will not receive any incoming authentication. Therefore, since that patch, you cannot coerce SMB client with a Marshall target information. So it prevents this vulnerability, but it also breaks the Kerberos relay primitive. A few words to conclude. This vulnerability showed that there are still a high impact, simple, and stable logical vulnerability. We found out that at the start it was an accidental discovery, but it was quite interesting to dig into that. And we think there are still more vulnerability like that. Also, we noticed that SMB signing is still underrated, because in that specific case, it blocks the exploitation of this vulnerability on the SMB service. So at least if you are performing hardening measure, you can still prevent some 0 days vulnerability. And sadly, the SMB signing is not enabled by default on Windows machine except the latest version. So we definitely recommend to at least implement it. Thank you, everyone. If you want more details, you can find it on our blog post. And if you have any question, feel free. And enjoy your meal.